prove theorem that if we have a subset of n vectors in an n-dimensional vector space. Okay, so we have an n-dimensional vector space, and we select a subset of size n, and this subset spans a vector space. Then this subset is a basis. Right. So the number is very important there. Because to be a basis, we have to show that this set spans the vector space. First thing. The second thing is we have to show that this set is linearly independent. So we have two things. But if we are considering a finite dimension vector space, means that the vector space has dimension n, and we find a subset consistent of n vectors, and this subset spans the vector space, then this subset must be a basis. So we don't need to prove the independence. Here is another version. Again, we have an n-dimensional vector space, and we find a linearly independent set, and this set consists of n vectors. Then this set must be a basis. Means that such a linearly independent set spans the vector space because the size of this linearly independent set is n. Okay? So this is another version. Now, a proof. Alright, so that is the right. So suppose there is a linearly independent. So we prove by contradiction. Suppose there is a linearly independent set of n vectors. And we such that S does not span then we can pick up a vector, say V, in V minus the span of. So we can pick up a vector. And then S union V linearly independent. Okay? By a theorem in section 2.4. So in section 2.4, I proved a theorem that if you are given a linearly independent set, and this linear independent set does not span the whole vector space, then we can pick up an arbitrary vector outside of the span, and then we can form a new linear independent set, and this new linear independent is bigger. So I believe you still remember this theorem, right? right? So since dimension 3 extend, there is a basis B for V. Okay? Such that V is equal to the span of size n V. Okay, so we can find the basis of size n for V. And we know now since contained in V, which is the span of V, and the size is n plus 1, which is bigger than the size of the spanning set. So S must be linearly dependent, right? By a theorem in section 44. We used that on Wednesday, right? Last Wednesday. So if you have a spanning set, span from a set of size n, then any subset in the spanning set has size bigger than n will be linearly dependent. Alright, so you have contradiction. Okay, that is a contradiction. So the contradiction is from this statement that we suppose there is a linearly independent set of n vectors such that S does not span V. So the assertion is that S does not span V. And from that, because S does not span V, then we can pick up a vector to form a bigger linearly independent set in the vector space. Okay? But on the other hand, because the dimension of the vector space n, so there is a basis of size n for V. And of course, a basis spans the whole vector space, right? So that this new linear independent set is a subset of the span. And so the number is bigger, right? This is n. The size of the new linear independent set is n plus 1, and this is bigger than the size of the basis. So this subset must be linearly dependent. So these two contradict to each other, right? So you get contradictory result. And the reason is because this is not true. So yes. Okay, so it's that. We prove that as a spaces. So if we have a linearly independent set, and the size of the linearly independent set is the same as the dimension of the vector space, then this linearly independent set is a basis. Any questions? Now we have three conversions of the previous theorem. So let's say if a set of 10 vectors spans a vector space, just suppose we have a set of n vectors. And this set spans a vector space V. Then the result is that the dimension of V will be less than equal to n. Without knowing the information of the dimension of the vector space, we just say, oh, well, we have a vector space, and we know that there is a set of n vectors which spans this vector space. Then what we can have is that the dimension of V will be less than 2. And the proof. Use contradiction. Again, suppose dimension V, okay, is bigger than n. So there is a basis V for V, right? With size equal to dimension of V. Well, I have to be a little bit careful inside. Suppose that a little bit tricky. I have to resolve the question that how do we know that the vector space is finite dimension? Given the condition that I have a set of n vectors, a span of vector space, then how do we know that V is finite dimension? Okay, so I changed my mind. I will use the direct proof. Otherwise, I will get trouble, right? Because I have to repeat. When I say that, okay, let me say what is the problem occur to me, all right? I repeat, don't write it down, all right? I just repeat what I have written. I have said, we suppose suppose that dimension 3 is greater than 10. Now, it's doubtful. Because how do you know this V is finite dimension? When I write it down, I have to make sure that V has dimension. Right? By our definition, to have dimension means that it is finite dimension, right? But we haven't looked at yet. So that but I can't make this because this maybe it's even so I cannot write it because I have no authority to write it down before I prove this finite. Right? So I change my mind. So what is that? How can I do that? Okay, I will use. Remember, I proved a theorem that you're moving a vector, right? So I work with this set. Okay, so let S be such a set. With size equal to n, and the V is the span. Okay? So we let X be such a set with the size is n and S span V. So now, if S is not linearly independent, okay? So if S is not linearly independent, there is sorry. I need the detail, sorry. So I have to set S and then span S. If S is non-linear independent, then there is a non-trivial. There is a non-trivial linear relation. Okay? On S. So the A1 0 with some I, right? Not some right. So we have a non-trivial linear relation on S, and so in here there is some coefficient which is non-zero. Then UI right? So UI is that? It's a linear combination so by removing UI from S. Okay. We still V equal to span S. Okay. By the theorem of removing a vector. So we proved the theorem before. So we can remove an element from the S, and then the resulted set still span V. Okay. So we continue removing vector one by one from the spanning set if it is not linearly independent. Right? So if the resulted spanning from the resulted spanning set no linearly independent. Okay. So if the resulted spanning set, right, is not linearly independent, we can reduce it again one by one, right? And we must start. Why? Because we have only n vectors in the original spanning set. So if we remove one by one, eventually it will become to be empty set. Right? So the process, since S is equal to n, the process will start. Okay, the process will start eventually. At most 10 steps. So if the process starts at n step, that means you remove all the vector in S, so S becomes an empty set. Okay. If it's empty set, then the vector space should be trivial. It consists only the zero space. So of course, the dimension is less than n because the dimension is zero. But anyway, so that we start at the most, and a subset we call subset Q and a linearly independent subset Q of S is resulted with V is equal to the span of Q. Because in each step, when we remove an element from the spanning set, that the smaller set still span the whole vector space, guaranteed by the theorem of removing a vector, right? By the theorem of removing a vector. So this is always true, right? And when we start the process, the resulting subset must be linearly independent. Because if it's not linearly independent, then we have to continue, right? Remove one vector. But this is when you start, because you have originally have only a vector there. So now thus Q is a basis for V. And then dimension of V is equal to the size of Q, which is less than equal to the size of and we have compressed proof. So this is called a direct proof because we construct a basis for the vector space. Yes, please.
那个summation 的系数是不是怪怪的？
Oh, yes. Thank you. They are A. Thank you. Thank you so much. Okay?
要加负号。
Yeah, minus sign. Yeah, really good. Minus, yes. Thank you again. Okay, so in this constructive proof that to find a finite basis for the V is just the intermediate result. So I don't need to worry about whether the vector space is finite dimensional or not. Of course, let me go back to the statement of the theorem. If the statement of the theorem says that, I change a little bit. If a set of n vectors spans a finite dimensional vector space, if I put finite dimensional here, then I can use the indirect proof as I tended to do, right? 20 minutes ago. If I put a finite dimension vector space. But since I didn't put a finite dimension, so I have a question about it. And so I have to change my mind to use the constructive way, the direct proof. And then the next theorem is about linearly independent state. It's a little bit tricky. So the statement is if there is a set linearly independent set of n vectors in a vector space. Then either V is not finite dimension or dimension of V is greater than equal to 2n. So I have to be very careful. Okay? Right. So if there is a linearly independent set of n vectors in a vector space, so suppose in a vector space I find a subset. The size of the subset is n, and this subset is linearly independent. Then either V is not finite dimension, or when it's finite dimension, because when I write the in this class, okay, in this class I assume V is finite dimension before I put the dimension, okay? Because when I define the dimension of V, is that when V is finite dimension, because we will prove a theorem. When V is finite dimensional, then all bases has the same size. We prove that. This is very important, you know that. And so that we define the dimension. But if a vector is not finite dimensional, we haven't had the idea up to now. I haven't mentioned how to define the dimension of that vector space. Okay. So my way to avoid this difficulty is that either V is not finite dimensional, so I don't need to consider it, and let it go in this case. But if it is finite dimensional, then I have to prove the dimension is at least n. Okay? So it's contrary to if this is at most n. If you have a spanning set, then the dimension is an upper bound. If you have a linear independent set of size n in a finite dimensional vector space, then the dimension of the vector space is at least n. The proof. Okay, so we only consider that the case that V is finite dimensional. Right? So we only consider the case. Oh. So we use the indirect proof. So suppose the dimension of V is less than n. Okay? Suppose less than n. Then there is a basis V of size dimension V for V. Okay? Because the size of the basis should be the same as that, because by the definition, right? And for V. Alright, so now let S be a linearly independent set in V with the size of S U N. Now, since S contained in the span of the basis, okay, and the size N is greater than the dimension of V, which is size 3. So S is a linearly dependent set. So now the contradiction. Because we say there is a because there is a linear independent set. So that is be such a linearly independent set with size with N. Oh, so I think I have to move this statement before here greater. Because this is given by the theorem, the statement of the theorem. So let S be such a linearly independent set in V with size. And now suppose the dimension V is less than N. Alright, so that is a basis V of size. Now since the set S is contained in V, right, and is in the spanning set of and we know that, so S is linearly dependent of condition. So that the dimension V is less than equal to is greater than equal to this is sorry. Okay, one more thing. Let it be a linear transformation from a finite dimension, just from an n-dimensional vector space through a vector space. Okay. Double. So V is n-dimensional. So V is finite dimensional vector space, but W can be infinite dimensional. May not be finite dimensional. So through a vector space W. Then the dimension of the range of T, which is less than equal to dimension of T. So we just talk about the range of T. Okay, so let B be a basis for V, because V is n-dimensional. So we can find a basis, right, of size n, right? Then TV, so what is TV? TV is the span. So TV, what is TV? So let's see. TV is T. Right? So the range is that. It's all the value of T, right, for all the vector in the vector space V. And this is T, A1, V1 plus A2, V2 plus plus AN, VN, and A1, A2, AN are scalars. Okay? Because every element in the finite dimension vector V can be written as a unique linear combination of the basis vectors. So it's that. Okay, and so because T is linear, right? So that this is come to A1, T, V1 plus A2, T, V2, T, okay? And this is just the span of the set of TV1, TV2, right? Then we set of that. So express the range of T as the span of this subset in W in the coordinate. And so the dimension of the range to the set is right? By a previous theorem. And this is n. So we find a spanning set for the range of T. Any questions? Okay, so let's take break now for 5 minutes. Yeah. which is finite dimension. Already know that. And suppose we have a set right? So suppose V is finite dimension, so we let the dimension to be n, and the size of the linear independent set is to be k. And the situation is here, so this is span of the S. From the previous theorem, we know that n is within k. Because we know that if we have a linear independent set of size k in a finite dimensional vector space, then the dimension of n has a lower bound, which is k, right? Okay, so if k equal to n, then S is a basis for V already, so we don't need to extend it, right? By a theorem. We prove that. Okay, so we prove. So if the dimension of vector space is n and we have a linear independent set of size n, then this linear independence must be a basis. So this is basis already. Right? So now if k is less than n, okay? So k is less than n, then in the span of this but not equal to V. Okay? Then this is from the same theorem, right? From the same theorem. So we can we pick up a vector V J plus 1 in V minus the span. And S union with K plus 1 is a linearly independent set. In So if k k plus 1 still less than n, we continue this process. Right? Extending the dotted linear independent set. Until 1 by 1. Continue by adding vectors 1 by 1 until a linearly independent set. Okay. So basically, if the dimension of the finite dimensional vector space V is n, and if the initial linear independent set is size k, in k is less than n, then we can add a vector 1 by 1 to the linear independent set and keep it, the resulting set, to be linearly independent in each step. 1 by 1, right? So add k plus 1, one more, and then so this one, and so the process is here. The next one, so this is V, k plus 1. Okay. And again, plus 2, and finally, okay, and we have that. So we add 1 by 1. And so this is same. And finally, so the procedure is 1 by 1 by 1. And every step is guaranteed by a theorem proved in section 2.4. Right? Until we have a linear independent set of size n, and this n is equal to the dimension of the vector space n, and we're done. Then S union of spaces over ducts. Okay, so this is a procedure. Okay. The next theorem is an important theorem in linear algebra. So let's see. So let's take a linear transformation from a finite dimensional vector space V to a vector space of. Then the dimension of the kernel of P plus the dimension of the range of P is equal to the dimension of V. We prove that the dimension of the range of V is less than or equal to the dimension of V, right? And then we can establish the equality by adding the dimension of the kernel. So the difference is just the kernel. Okay? Because in a previous theorem, we proved that the dimension of the range of P is less than or equal to the dimension of V, right? But now we can prove that by adding the dimension of the kernel of P, we can do this. Right, so the proof. Right. In a previous theorem, we have the dimension of P shown that the range of P is finite dimension. Okay, it's finite dimension. And so the important thing is the dimension the implication is that the range is finite dimension. Okay. Right. So relate. This is equal to m. Okay. Let's find the answer. Also, since since kernel P contained in V, okay, and let me just use that dimension. Because K. So the kernel T is also finite dimensional. I think I haven't proved that yet, right? So if I have a finite dimensional space, then any subspace is also finite dimensional. Yeah, I think I haven't proved that before. Let me finish that. Okay, I use it's of course it's true, but I haven't proved that yet. It's fault. But that's fine. Let me just use that to complete the proof. Alright, so they are all finite dimensional. So let I think I need a hint. Okay, so that W1 Okay. The basis for the kernel P and the let W the basis for the range. Okay, so we have, because they are finite dimensional, and we say the dimension of the range is M, the dimension of the kernel T is K. Okay. Since each term as in the range of T, there exists UI, VI, such that So now we claim that U1 up to UK, U1 up to Vn is a basis. Okay, well, our claim is so the extension there. Okay, so the first part is that let V in V. Then TV, okay, it can be written as the beta 1 of NTV and so the image can be written as because step 1 up to step m is the basis for the range, right? So we can find this way. And but tau I is t v1 plus beta m v un. So this is t beta 1 v1 plus beta m vn. So TV is equal to T of this linear combinations. So we have TV minus beta 1 v1 equal to 0. Okay, so we move this. Go to the left hand side, right? And the linear will appear again. So we have this one. So V minus beta 1 V1 plus is in the kernel. So we find that it's a kernel. So V minus beta 1 V1 plus beta m Vn. Right? It's a linear combination of the basis vectors for the kernel T. So this is alpha 1 V1. Okay. So finally, the V is alpha 1 V1 plus alpha k UK plus beta 1 V1 plus beta m V1. So that V is in the span of the set here. V1. Okay, 1, okay, so it's a spanning set first. So we know that this is a spanning set. The first step. thing we have to prove that this is a linearly independent set. Right now, consider an arbitrary linear relation. So consider alpha 1 plus alpha k uk plus beta 1 v1 plus beta m vm equal to 0. Okay, so now we consider an arbitrary linear relation on this set. We have to prove that all the coefficients should be 0. How? Zero, right? Now, taking P on both sides. Prime. We have to set applying P on both sides. We have alpha 1 P u1 plus alpha k P uk plus beta 1 P v1 plus beta n P equal to P 0, which is 0. And now, this is 0 because ui's are in the kernels of P. So they are all 0, then your vector. So we have beta 1, and this is W1, this is Wn. Okay, right? So we have beta 1, W1, plus beta m, Wm equal to 0. But W1, Wm, but they form a basis, so they are linear independent. They are linear independent. So that means that beta 1 up to beta m 0 since linear independent set. So we know this all zeros. So we know they are units. Okay, so we already know beta 1 up to beta m are zeros. But now we have alpha 1 u1 plus alpha k uk equal to 0. Right? Because we already proved beta 1 up to beta m are zeros. So they are zeros, and from this linear relation, we know alpha 1 u1 plus up to alpha k uk is 0, and this implies that alpha 1 they are all 0 since u1 up to uk is a linearly independent set. Okay, so now I prove all the coefficients are 0. So the conclusion is that u1 up to uk, u1 up to un is a linearly independent set. Alright, so that in here that V is equal to the span, right? And the set is linear independent. So V1 UK V1 Vn is a basis for V. That's dimension of V is equal to K plus M, which is dimension of the kernel of V plus the dimension of the range. So for any linear transformation from a finite dimensional vector space V to an arbitrary vector space, then the dimension of the kernel of T plus the dimension of the range of T is just equal to the dimension of the domain. And this theorem has many important consequences. We'll see that. All right, an application of this theorem is here. So consider for any M times N matrix A. Okay? The rank of A plus the nullity of A is equal to N. The number of columns of A. So this is called the rank nullity theorem. So let me make a remark. Rank of A, you know, there's a lot of interpretation of rank of A, right? It is the number of figures in A, okay? And it is also the dimension of the column space of A. The nullity is the dimension of the null space. Okay. So maybe I will say dimension of the column space. Okay. So the rank of A by the initial delineation is the number of pivots in A, right? In chapter, I think chapter 1 to chapter 2, that number of pivots, and actually it is the dimension of the column space of A. And the nullity of A actually is the dimension of the null space of A. So in the proof, define a linear transformation. The matrix A defines a linear transformation from N to M by a linear transformation we call P by P V. So this is so any, we know that any matrix M by N matrix will define a linear transformation from the n-dimensional Euclidean space to m-dimensional Euclidean space. And by this, right. And now the kernel of E is just the null space of A. Okay? We know that before. And the range of the linear transformation is just the column space of A. Okay? So now the dimension. So we know the dimension of the kernel of P plus the dimension of the range of P is equal to the dimension of the domain. So take from the previous theorem, right? We have that. Okay? So that we have dimension of the null space of A plus the dimension of the column space of A is equal to N. And by our remark, this is just called the nullity. So nullity of A is just the dimension of the null space of A. And the rank. Okay. So this is just the dimension of the column space. something here, because that before we because before we define the rank of A is by saying that the number of pivots in A, right? So so this is what we need to prove. I haven't done it yet. I have mentioned, but I haven't proved it yet. Remember at the end of last section that I'm saying that I make a remark. So, well, I will say that later. But so I need to verify this one. Okay. But anyway, is that the dimension of the column space, because the column space of A is just a range of A, right? We know that already. So, and the kernel of P is just the null space of A. So, because that we define this is kernel of A2, right? We use the kernel of a matrix or null space of a matrix. So now I have to add one more theorem. The pivot column of a matrix from the basis for the column space. I think I stated the theorem without proof, right? I promised to give you a proof, but I haven't given to you, right? So the pivot, okay? The pivot, you know that so let U be the reduced row echelon form of A. Okay, so H here. So U is something that say maybe in general, one here, something. Okay, so so this is the reduced echelon form of A. And a pivot column is that we know that we have a pivot position in the second column, right? So the corresponding second column, let me say, okay, so let's see. Now, because the second column has a pivot, the first column has a pivot, so that this is a pivot column. They are called pivot columns. Okay, you understand that? The correspondence. If I have a pivot in the reduced echelon form in a certain column, then that column will be called the pivot column. Is that okay? Are you good? Good now? We'll go back to chapter 1. Okay. Now, Now look at the columns of the pivot columns. Look at the pivot columns here. You can see that the pivot column, okay, the pivot columns in U form a linearly independent set. Why? Why? Because you can see that the first pivot column cannot be represented as a linear combination of the so maybe I take the example here. Probably just this example. Okay, so 1, 2, 3, 4, 5, 6. More specific. So the last one are pivot columns. All right. So we have 3 pivot columns right here. Now the pivot columns in U form a linearly independent set. Why? Because you see this column, because pivot columns they are standard unit column, right? 0, 0, 1, 0, 0, 1, 0, 0, and 1, 0, 0, 0. So they have only one, but other entries are all zeros. And the 1 are in different locations. Can you see that? So these pivot columns form a linearly independent set. Okay? And so this is alright. So now the columns of A, a linear relation x1 a1 plus xn n equal to 0 the columns of A, right, and it was to correspond to a similar linear relation on the column of U x1 u1 plus x and un equal to 0 with the same coefficients. x1, x2 up to xn. Why? Why? a linear relation like this one. X equal to okay? It's a homogeneous equation. And the kernel of A equal to the kernel of U. Because when we want to solve the kernel, means that we want to know if there exists any non-trivial linear relation, right? Right? It's the same as we can apply the operations on it, right? And so the solution, if we have a solution here, it's the same as the solution of these homogeneous linear equations. Remember that? So we use that to find the kernel. So basically, when A and U is the reduced or echelon form of A, then actually that they have the same kernel. And so if I have a linear relation on the columns of A, I have a corresponding linear relation for the columns of the U. And the coefficients are exactly the same. Now, okay? This is we apply the operations to solve the kernels, to solve the homogeneous linear equations. So this is from chapter 1. So now we already know that the pivot columns will form a linearly independent set. We already know that, right? From here. Because they are just standard unit vectors. They are just standard unit vectors. Right? So they are just standard unit vectors, and the pivot position are in different rows here. So of course they are linearly independent. Okay? So we know that this is the pivot column. And also I can make more, and the non-pivot column are linear combinations of pivot columns. Alright? So we have two things. The pivot columns will form a linearly independent set as well. And non-pivot columns, for example, like this one, okay, because they are linear combination of pivot columns, right? Because the pivot columns are standard unit vectors. Okay, so you have 1, 0, 0, 0, 0, 1, 0, 0, 0, 0, 1, 0. And all columns with cross here they are linear combination of these three columns. Because they can be formed by the standard linear combination of the standard unit vectors. Okay. And the rest, we have zero rows here. After the last pivot here, we have all zeros in the rest of the coordinate position. So this is our observations for a reduced log echelon form, because it's so simple. So we can identify these two facts here. Is that okay for you? From looking at the reduced log echelon form. All right. Now we know that the linear relationship on columns of A has a corresponding relationship on columns of A. So now the non-pivot column. So every non-pivot column here. So now we can state that so the pivot column in A form a linearly independent. Right? And the non-pivot column are linear combinations of pivot columns. Okay. Okay. This is because that if for the pivot columns, to find a linear relation for the pivot columns, we can set the coefficient of the non-pivot column to be zeros, right? And if the pivot columns of A are linearly dependent, then we can have the non-zero, not all zero coefficient to set up a linear relation. But this corresponding to a non-trivial linear relation. So this is a contradiction. You can't. So you can compare each other. So for example, if let me see, if I write down a linear relation for the pivot columns here, say alpha A2 plus beta A4 plus gamma A6 equal to 0. If I write, suppose I have a linear relation for the three pivot columns, then correspondingly I have alpha, the U2 plus beta U4 plus gamma U6 equal to 0. Right? So if I have a linear relation for A2, A4, and A6, I must have a corresponding linear relation for U2, U4, and U6. But because U2, U4, U6 are linearly independent, so alpha, beta, gamma must be 0. Implies alpha, beta, gamma must be 0. So A2, A4, and A6 should be linearly independent. Is that okay? So the linear relation is very important to see here. This is the very deep inside of the law operations, the law of this echelon form. We come up to this point from time to time. So that is the situation. Okay, and also that if every a pivot column, for example, for here, I have, we know, so we know that in here, we know the U5, U5 here, right? So U5 is cross U2 plus cross U4, right? So U5 is a linear combination of U2 and U4. Now, can you see that? Okay. So now, correspondingly, A5 is equal to cross A2 cross A4. Okay? That means that this now pivot column is a linear combination of the pivot columns. Okay? So all this from here, this is the very big things we have to know. All right, now, because now the column space, now, the column space of A is the span of A1, A2, up to AN. And because non-pivot columns are linear combination of pivot columns, you can delete, right? Removing a vector, the theorem of removing a vector, right? You can remove that non-pivot column out from this list without change this result. Okay? So gradually you have span and this is pivot columns. So the column space of A is spanned by the set of all pivot columns. And we say that the pivot columns form a linearly invariant set. So that the set of pivot columns of A is a basis for columns of A. And how many pivot columns of A do we have? It's the number of pivots we have. So it's equal to the rank. So the dimension of the column space is equal to the rank of the matrix. Alright, so I end the proof. The proof is not very trivial, you know. It's not trivial. But so that I have to put it at the end of the lecture. Because the material used here, have to go back to chapter 1. As I said from the beginning of this semester, I said the operations always your good friends till the end of this semester. Okay, I will use the operations from chance to chance to go to the deep inside. Even though it's very simple, but it is profoundly important. Alright, so I stop here.